right, so it begins. This is a Jacob does acid ionization problem in the attempt of getting Henry Le Chatelier's attention so he can help me with my test in a couple of days. Liam, do you have anything to say?
No.
Oh yeah, how could I forget? It's featuring Liam Cunningham. He's a chemistry prodigy, by the way. He's like the next Henry Le Chatelier. So.
Yes,
He could solve this problem in his head. No calculator.
Yeah, if my head includes Google.
Yeah, I mean, yeah. So anyway, let's start. This is basically like a minor buffer problem because if you notice, you're adding a small amount of your base. This is a salt, but it's also like slightly basic to a weak acid, hydrofluoric acid. It's weak, and you can tell it's weak. I mean, you should be able to just identify that, but you can tell it's weak because it has a Ka value. Anything with an acid ionization value means it's weak. So yeah, that's just something.
Yes.
So, William, what do you think the first step into solving this is?
Make an equation.
See, he's brilliant. That's exactly correct. I'm going to do that right now.
Epic.
Yeah, so the first thing you want to do, I don't know why I made a PDF. Yeah, so the first thing you want to do is make that equation. And basically, William, can you maybe tell me what the equation is?
No, you'll never summon Henry if you rely on me for everything.
Fine, then I'll do it myself. So the two chemical compounds that we have are, it was hydrofluoric acid, right?
Of course.
Which is the weak acid, by the way. Plus your sodium fluoride. And what they produce would be basically just each other. They're going to produce like spectator ions. What they produce isn't that important just because the volume isn't changing. So it's not that important. But what is important is these two. Liam, can you remind me how many moles of the hydrofluoric acid we were given?
A certain amount.
That's right. It was a certain amount. It was like this much, I think, more.
Yes.
And we were given about, I think it was 0.009 or something. I don't remember. Yeah. And it was in 1 liter of water. It was like, or sorry, it was in, the volume of one of these was like 1 liter. So concentration doesn't actually, concentration technically is the same as moles because it's like saying this divided by 1. So it's like the same thing. Anyway, we need to find out how much is consumed in the reaction. So to do that, right, this gets all used up because why? Because this is the limiting reagent. because this is the lesser amount of moles in the reaction. But if this is the only thing that was used, right, then both of our reactants use the same amount. So you're just going to subtract this amount of moles from both sides, and you're going to get, I think it's, Liam, are you still there?
Yes.
Can you check if this is correct?
Looks correct.
Yes. Anyways, this is in molarity. But because, you know, there's 1 liter, so technically it's also in moles, but like, the point is this is our initial concentration, because look what's left over, the weak acid, right? So next thing we're going to have to do is we're going to have to ionize it. So in other words, we're going to have to add the water to conduct hydrolysis so it's ionized correctly. Because if you remember, this Ka value goes like this. Here, I'll just like write it out. So it's your hydronium, right? It's your hydronium. Just imagine brackets around that. I don't feel like drawing them. So it's hydronium times your base. This is the base over the weak acid. So in order to get all of these ions, how they are, we have to add the water. So it's going to be like this. So we're going to make a second reaction. Do you think we'll summon Henry with this thing?
Hopefully.
Oh wait, that's so much faster. Bro, I'm just using my finger.
Epic.
All right, Liam, can you tell me which one is which one of these is the acid in the base?
The first one.
Is what? Which one?
The first one.
Is what?
Option 1.
What?
Option 1.
Oh, so you're saying this is the acid? That's brilliant. And by process of elimination, this must be the base, right?
Correct.
Well, Liam, I'm so grateful. Anyway, this is the acid. Right? And this is the base. So what this means is that this is going to take this one. So the water is going to take the acid's proton, or H, and add it to itself. So the new equation will look like this, right? So this loses its H and becomes F minus. F.
F.
And our conjugate acid is now the hydronium. And now, you know, looking back at our acid ionization equation, you can really just see like how it's lining up, right? Because over here, you never include water because water is, it's not part of the ionization because it's liquid. It's a pure liquid, so you don't actually use it. But over here, you have your weak acid on the bottom because when you do this, remember, it's products. Equilibrium is products over your reactants. Because we don't include this, it's just like saying that the weak acid is on the bottom and then these two are on the top. So now we have our Ka complete, but we're missing something. Liam, what are we missing?
Something.
Can you be a little more specific?
No.
I think what Liam's trying to say is we're missing an ice table, because this is great. We now have, everything we need technically. Like, we have the equation all sorted out, everything's in agreement, but we don't have any numbers. We can't actually solve for anything. We have this, but we don't have the x. But we can find the x. It's not that bad. So I'm gonna erase this stuff. Like, I'm gonna erase. I'm gonna erase this stuff like up here, but I'm gonna keep this equation, and you're gonna see why. I just need to figure out how to erase stuff. I wish I had an actual board software where I could just erase everything at once, like in Photoshop.
Epic.
Yeah. So, oh wait, that's brilliant. All right. Anyway. So I'm going to do an upside down ice table. It would be the same if you did it on the bottom here. I just don't have any space. So we're going to make the ice table kind of funky. But, what I'm trying to say here, you're just going to make an ice table. Okay. So remember before we calculated our initial concentration of the weak acid. Or we know that it's going to lose some because it's being consumed. You know that equilibrium can be used to combine basically. Doesn't matter. This, we don't know, like, we weren't given any information about how much was put in. So we're going to say it's 0, but we do know that some of it will be produced. So yeah, and then plugging this back into our Ka expression. And we know this, it is given 7.1 to the -4th. Fourth. And a neat trick with acid-base titrations is you can pretty much always assume that this X is really, really small and it doesn't actually impact this. So you can just say it equals 0 pretty much. That's almost always an acid-base titration. Not in all, actually this is not a titration, but we're gonna solve it anyway and we'll check if this is fine. But in acid-base titrations, you can, but this is not an acid-base titration, this is a buffer. So anyway, gonna cross multiply, so it ends up being x squared, right, equals this. 10 to the negative 4. Just imagine that's a negative 4. To like this. Yeah, I'm actually just gonna tell you the answer because I don't feel like plugging that into the calculator. So I already did this one. And for x, I got x equals 0, 0, 0, 8, 0, 4. Liam, are we done?
Yes.
Liam. Are we done, Liam?
No.
Why is that? What last step do we have to do?
The finishing maneuver.
What?
The finishing maneuver.
Yeah, that's right. We have to calculate for pH. So this right here, this is actually a concentration of our hydronium, because remember, look, hydronium is X. At equilibrium, it equals X. So whatever X is, it's the same concentration as our hydronium. So what do we have to do, Liam? Yeah, I'll give you a hint. Liam, what do we have to do?
Find the answer.
That's right. We have to take the negative log of the concentration of X, or which is also the same as hydronium. And we're done. We should have pH. I'm not going to bore you with me plugging into the calculator, so it's going to be like something like this, but then you can round it up to 2.1. That is our answer. pH is 2.1. Okay. We're done.